Imagine that you're asked to guess a number that's in some particular range. For example, the range of numbers between 1 and 99. You're allowed to ask questions which have yes or no answers, like is the number 15 or is the number greater than 2? And you get more points for guessing with fewer questions. So, in these conditions, what's the best strategy that you could take to try to find out what the number is, and why is it the best strategy? Thinking about this situation will help us to think perhaps in a slightly different way about searching for something in an array or a set of data, and maybe escape the category of behavior that we were looking at before that has linear performance. We might be able to devise a strategy that could give us a better category of performance that handles larger amounts of data with fewer comparisons, fewer steps, fewer operations. So think back to this problem I've described, guessing a number in a range where you're allowed to ask yes or no questions, and what gets you the fewest number of questions to be able to find that number with no other knowledge besides the range that it might belong to and the answers that you get from those questions. So pause the video for a moment and think about what approach you might take to that problem. One approach that can be helpful in situations like the one here, where you've got some range of things, is to ask questions that split the range. So ask questions that allow you to know that the number is in sort of an upper half or a lower half of the range. For instance, instead of thinking about just the range from 1 to 99, what if we thought about the range from 1 to 50 and 51 to 99? And we ask a question like, is the number larger than 50? So if the person answers yes, then we know that the range for it is 51 to 99. And if they answer no, then we know that the range for it is 1 to 50. And that gives us half the numbers eliminated with a single question, rather than questions like, is the number 1, is the number 2, is the number 3, which would follow more of a sequential kind of approach like we've looked at before. So then we can do with whatever range is given to us. If they said yes, for instance, then we're left with 51 to 59, and we can do the same thing, 51 to 99, and we can do the same thing with, say, 75 in there. So treat that as 51 to 75 and 76 to 99. These may not always be a perfect split right down the middle, but they do get us pretty close to having half of the data narrowed down before, or just based on a single question. So we ask, is the number larger than 75? And that gives us this new range, possibly of either 51 to 75 or 76 to 99. And we can keep doing this same thing based on whether they say yes or no. Then we've got half the range, and it doesn't matter which answer they give because we'll have narrowed down to half the data, either the lower half or the higher half each time. So this cuts our data in half each time we ask a question. And this kind of approach can actually be used in search as well. If we have our array or our set of data that we're asking about, then we can aim to narrow that down in half each time that we do a comparison, if the data is sorted already. And that's going to be a very strict restriction on us here, that we have to have data that's already sorted. Some of our optimizations for sequential search also relied on this, so it's not completely unreasonable. There are approaches that you can take when it's not sorted, and you can certainly look at those, but this gives us a new category of search. And here's the reason why. When we do a single comparison, instead of only looking at a single item, so in this range from 1 to 99, instead of having to look at 1, then 2, then 3, or in an array, rather than having to look at index 0, index 1, index 2, etc., we look at the middle index and we ask a question about it. Is our number less than this, or is our number greater than this? Should our number come before this, or should our number come after this? This works for strings. It works for any orderable, sortable kind of data. And this is called binary search. So binary search is on a sorted list or sorted set of data, on sorted data, such as an array, do a comparison with the middle value. So the item at the middle index in the array, for instance, if the middle value, if our search value is less than the middle, we look at the lower half of the array and repeat the process. If our value is higher, then we look at the upper half of the array. So if the search value is greater than the middle value, then we look at the upper half of the array. If search value is equal to the middle, then we return that middle thing. We've found what we were looking for. If the search value is equal to the middle value, then we return the middle value. It's worth noting that a lot of the search sort of things that we do here are useful for when we have some information that we're able to use for lookup, but more complex information that we're finding when we get there. For instance, we might use people's social security numbers to look them up so that we can find their bank record or their student record or that kind of thing. Most of the examples we use will just show integers or just strings. Think of those as the lookup tool for finding something more complex. So think of those as being like account ID numbers or social security numbers or phone numbers or things like that. So then if the range has more than one number in it, then we repeat. So we, in either of the cases where we are given a range, then we'll repeat the process on that range. When there's only one item in the range, then our search value will be, then the middle value will be the only item in that. If we come down to an empty range, there's nothing left, then we can say that that search value was not in our array, was not in our data. So the reason it's called binary search is because we ask these yes or no questions that cut the data in half each time. We've seen examples before where we cut the remaining things in half each time, like our finding the fake coin example when we were first looking at recursion, and we were able to eliminate half the coins and half the coins again and half the coins again. That gives us this kind of behavior pattern where we see, for instance, that if there were if there were two values in our range, then we would be able to answer with one comparison. Let me insert a table here. So if there were, let's see, range size. If our range size was 1, pretty obviously we would need to do one comparison. or question in my example up here, if our range size was 2, then we can get our answer with at most 2 questions. We might have to ask, is it lower than the first item? No, then we give the second item as a result, and so on. We could actually do it in one comparison in that case, because we are able to conclude that the answer was the other number if they say yes or no. I guess checking that it's the exact thing might count too. So we can do it in 2 comparisons, 1 comparison, about that amount. If we have about 4 items, we can split to the lower half or the higher half, and then we have 2 remaining, and so that gives us only 1 more question. So the number of comparisons or questions for 4 items will be 2. You can also think of this in the other direction. If your range of what was of size 16, then with only 1 question, I can narrow it down to 8 numbers. If there are 8 numbers with only 1 question, I can narrow it down to about 4. And if there were 4 numbers, I can narrow it down to about 2. And if there were 2, I can narrow it down to about 1. And then when I only have 1 remaining, I can just look and see if that is my number or not. So when I've got a range of size 1, I'm always able to just immediately look and see if it's the right thing. So now we can see that for 8, it would take 1, 2, 3 comparisons. And for 16, it would take only 4. And in fact, we can get very large numbers and still have very few number of steps that we need to do for them. So 16 gives us 4. 32 would give us would require 5 comparisons. 64 would require 6. 128 would require only 7 comparisons, versus our sequential search, which was O of n, which took for 128, for instance, would take something in the range of 128 comparisons in the worst case. So we might get lucky, and our middle number might be one of them, and our middle number might allow us to eliminate 1 more number each time or that sort of thing, but roughly, these are the number of comparisons, or in our example above, these are the number of questions that we would have to ask to be able to answer that or find that secret number in a range of size 1, a range of size 2, etc. So this kind of pattern gives us something that's O of log n, because what we're really answering, or what we're really asking, is what power of 2 gives us a range of this size? 2 to the first gives us a range of size 2. 2 squared gives us a range of size 4. 2 to the third gives us 8. 2 to the 7th gives us 128, because you can sort of do this backwards. We have narrowed down the range by dividing by 2, dividing by 2, dividing by 2. So I'm asking, how many times must I divide n by 2 to get it down to 1? Right? That's essentially what we're doing here. There's another way to ask that question, which is, what power of 2 is equal to n? That will answer the same question as these. And there is a mathematical function that tells us the answer to that question. It is log base 2 of a number gives us the power of 2 that gives us that number. So log base 2 of n gives us the answer to that question, which is, what power of 2 is equal to n? So the number of comparisons, or the number of questions, will be log base 2. This means that this method is O of log n, which, as we can see, is a much better performance category than the linear types that we've been looking at. Even those optimized linear approaches, even those optimized sequential searches, could not get nearly as fast as an O of log n approach can take to this. So you'll dig further into these concepts and maybe get a little better grasp of this kind of behavior as you look at the example of binary search in sections B and C of the activity today.